we welcome Tim Lantzsch from the Fraunhofer ILT. He's a group leader in the powder bed fusion group. The ILT is usually known for being a key player in powder bed fusion, being the very first among in this field, having filed the key patent about 30 years ago. So we have quite the history also here on stage. So Tim, thanks again for joining us again after having you as a speaker already last year. We were looking forward a lot to the advances he has made.
Thank you, Andreas, for the introduction. So for history, at least for me, it's not 25 or 30 years, obviously. But thanks for having me again, and I'm glad to show you our latest results on processing with the AFX laser, but this year focusing on new materials, especially when you think about powder bed fusion. Material range is still a very, very relevant topic. So most of the materials that are commonly used right now are derived from casting, milling, and so on and so forth. And of course, the customers demand materials they know from conventional manufacturing techniques. I will start things off with a short introduction of the topic and why we investigate especially hard-to-weld materials, high hardness, high temperature strength. Then we'll give you some insights in the machine and how we have modified also our setup to accommodate processing these materials. We'll give you some insights into our process development for one specific tool steel, and then we'll also give some summary and an outlook what we aim to do in the future with this technology. So as I mentioned, hard materials, and today's talk will only focus on steel, especially tool steel, is highly relevant. On one side we have distinct features that we can use from additive manufacturing to really generate highly complex and functional parts. And on the other side, we have characteristics of steel such as high hardness, high wear resistance, excellent properties for high performance applications. And to bring these aspects together is one of the key challenges that we are currently facing in powder bed fusion. So when you look at tool steel, very commonly used word, tool steel doesn't necessarily always mean tool steel. There is a variety of tool steels that can be categorized according to their hardness, of course, and also to their maximum operating temperature. So when you look at this graph, you see there is cold work tool steel, which is fairly good in terms of L-PBF processing, but lacks the properties, especially at elevated temperatures, and loses its hardness over the temperature. For hot work tool steels, there are also some examples that can already be processed at elevated preheating temperatures, such as H11 or H13 tool steel. Those are fairly good in terms of the hardness over temperature curve, but of course their maximum hardness isn't as hard, so that you can use it for tooling applications such as thread mills or such features. And then when you look into the materials that are commonly used for cutting applications especially, you see that especially ceramic materials such as boron nitride or tungsten carbide-based cutting materials are state-of-the-art for a lot of cutting applications, just because they are very hard and therefore can be used to cut a variety of materials or to mill a variety of materials. But one of the key disadvantages of these ceramic materials is that they are very brittle, so tool failure is usually catastrophic. So either your tool breaks or it works. There's not a lot in between. What is actually quite interesting is the high-speed steels that are also shown in the curve. Those are not as hard, but have fairly good impact toughness, for example, so that they are a bit more ductile in terms of the applications. So to give a short summary of the material we are targeting, high-speed steel, very good hardness, especially at elevated temperatures up to 600 degrees C. But in terms of L-PBF processing, a nightmare. high carbon content is usually classified as non-weldable, so very challenging to process via powder bed fusion. And that's what we are aiming for. So when you look at cut sections from these steels or even entire parts, depending on the process parameters, the geometry, you can end up with one of two things. Either you have a lot of hot cracks that form during solidification, or you end up with large cold cracks when you cool down the parts after the build, and then have cracking of the entire part. In some cases, as you see, several millimeters of deformation just due to cracking. And these result from the complex temperature fields we have in powder bed fusion. So usually you have quite regular heating and cooling cycles which happen very fast. You have discrete solidification and therefore inner stresses that can build up and then as a consequence lead to these defects in the component. What we did to address this topic is we used one of our lab systems. This is an Econity machine, very flexible. You've seen it in the previous presentation. Very good work to work in the lab. What's special about this machine is on one hand side that we can preheat the build plate up to 800 degrees C for these hard-to-weld materials on a reduced build volume of a diameter of 100 millimeters approximately. And on the other side, we have an optical system that allows us to have two laser beam sources that can be combined via a beam switching unit. And I will show you the schematics in a bit. But this gives us the opportunity to really have a side-by-side comparison of single mode fiber laser and the AFX in terms of exactly the same processing conditions that we have in our machine and just altering the laser source and the intensity distribution respectively. Additionally, we also have our monitoring systems installed. We have a modified chamber cover that we can equip with a thermal camera, but also a process camera to observe the L-PBF process, to control the actual layer temperatures over the build, to see if we have some kind of overheating or if the preheating system is actually delivering the temperature we are setting it to. This is quite useful if you want to maintain homogeneous processing conditions. If you imagine building up a larger component and you just set the base plate temperature constant and build the part, most likely the temperature in the active layer that you're currently processing will change because the distance between our heat source, which is the plate, and the active layer becomes larger and larger, and you have to think about measures to compensate these losses. As I mentioned already, we have a beam switching system in our machine that allows us to select one of two laser beam sources, one being our AFX laser, which yields beam diameters between 130 and 340 microns, depending on the AFX index setting we are using. And in our first beam path, we have a standard single mode fiber laser, which yields a beam diameter of around 75 to 80 microns. So more or less towards the state of the art as it is in most machines right now. Of course, we need to check that it actually works. We have done full characterization of both beam paths. So for the single mode and the AFX, we analyzed laser power characteristics and the caustic. We found that both intensity distribution and laser beam diameter were as expected, so 80 microns for beam path 1, so the single mode fiber laser, and beam path 2 in between 130, here for the index setting 0, and 340 for index setting 6. Then when it comes to the experiments, we first did some baseline experiments, so state-of-the-art Gaussian beam, preheating, temperature variation, and build-up of multiple specimens. We have some software tools in-house to analyze the cracks that are forming during processing, and are then characterizing the crack density, so the amount of cracks or the cumulated length of cracks per square millimeter, centimeter, however you want to put it. So there you can see that for all the different layer thicknesses, preheating temperatures, and also energy densities, you will in some way end up with cracks. You can have more cracks or less, depends. At room temperature it's mostly cold cracks, and then when you go up in temperature it's mostly hot cracking, but you are hardly able to produce crack-free or technically crack-free specimens. And then what we found in this, as a part of these baseline investigations, was that the amount of cracking really heavily depends on the geometry of our melt pool. So you end up with rather little crack, or next to no cracks, when you have a very shallow and wide melt pool, and you will end up with a lot of hot cracks, especially over several layers, when you have some very deep and narrow melt pools that commonly occur in what we call transition mode welding, so which is quite common for standard L-PBF processing parameters, because you want to, you continuously remelt multiple layers, and this is not necessarily good for inner stress buildup and hot crack formation, especially for this high-strength steel ASP 2012 material. So we figured out it would be very useful to do some additional tests based on the results we already had from the AFX. So we already knew that we can generate very nice and flat melt pools with it. So when you look at the graphs, even compared to the defocused Gaussian beam, similar diameter, you end up with a much wider melt pool, similar depth, which gives us enough leeway to have robust processing and do not end up with a lot of defects due to lack of fusion, but sufficient width, and the width to depth ratio is quite small. So we thought it is favorable to also run the AFX tests on this setup to see if we can even bring down the crack density more when we modify our intensity distribution. So as a last step, I've brought a video of the process with the AFX laser that we ran, I think, beginning of last week. It works well. It's a really nice process. I haven't got the results of the crack density yet, because you can imagine the material is very hard, so cutting the material from the plate, doing the cut sections, the analysis is quite challenging. You have to find suitable tools to even be able to cut the material, because this is usually used to cut other stuff. But first impression is the process works fine. We will do in detail analysis, melt pool geometry versus crack formation, and we really see a lot of potential in the additional degrees of freedom the AFX technology brings when it comes to processing of these hard-to-weld materials that are very sensible when it comes to the temperature fields and the continuous remelting that usually occurs in L-PBF. We have now got the machine set up. We have everything set. We have the opportunities to do a lot. And where we see the next steps in this project is we really see a huge benefit in processing of hard materials, which are usually hard to weld as well, because they can be used in tools to adapt, for example, cooling channels in thread mills or other milling components. Through the degrees of freedom we have in the design. But of course the cracking is a major challenge when it comes to manufacturing components out of these materials, and the potential for AFX we see at the moment is obviously that we have additional degrees of freedom apart from preheating to very high temperatures or modifying just our laser power scan speed and hedge distance accordingly. We also have the control of our intensity distribution, which then helps us to control the solidification conditions and therefore reduce cracking in these components. So that's it for my talk. Thank you very much for joining. Thank you for the attention. I'm glad to answer your question if you have some. Apart from that, you will feel free to join us in our booth. We are in the next hall, directly in the middle, basically. And yeah, thanks for having me.